Okay, so last time we were discussing chemical equilibrium, and we extended it from an ideal gas to a real gas. And essentially, you can use the exact same thing for a real gas that you did for an ideal gas, but the chemical potential or partial molar Gibbs free energy is slightly redefined to be the normal standard partial molar or Gibbs free energy or chemical potential, same difference, plus RUT log, but we got this extra fugacity coefficient here. And so that is really the only difference is you need to compute these fugacity coefficients and insert those into the Gibbs free energy if you want to do chemical e- uh, equilibrium. And so we basically went over how to compute those in terms of a departure function um, of the chemical potential. And this is a horrible, nasty derivative here. This derivative here is not too bad and is much more doable than this derivative here. So you can use Maxwell's relation and just show that if we are holding temperature constant, because again that's how the departure function is defined, is you are correcting for real gas volume effects at constant temperature. You can just basically integrate this. So, and in terms of the concepts learned, that's really about it for equilibrium. Now it's just a matter of showing an example of how this is used. So we just have a hypothetical example here. We have a piston cylinder device. It has inside of it 1 kmol of carbon dioxide, and it's fixed at some pressure and temperature. Okay, and we are assuming that CO2 is going to dissociate, meaning that the CO2 itself is actually going to fly apart into CO plus 1/2 O2. So sort of you could think of it as it's that what produced the high temperature and pressure in the cylinder was the combustion of say CO and oxygen, and now we're just basically finding out where it's sort of happy equilibrium spot is, but we are holding temperature constant, and so you could imagine that to hold the temperature constant, we have some sort of heat source that is adding energy or removing it from the cylinder. But since we're dissociating CO2, this chemical reaction here, where we take CO2 and split it into two pieces, is highly endothermic. So if we break apart any of the CO2 molecules that are inside of this vessel, that's going to require a whole lot of heat. And so you could imagine designing or a problem where then I would ask what the equilibrium mole fraction is and then what the heat supplied is. And we'll assume in general that the pressure could be high enough that we need to consider real gas effects. Okay, and so step one for these problems is first, based on the starting number of moles of material in your device and the chemical reaction, right here, we need to write expressions for DNI, because that is the condition for chemical equilibrium um, um, in terms of a reaction progress variable. Remember, a reaction progress variable epsilon. Epsilon is 0 if we are all the way at the reactant state, and if epsilon is 1, we are all the way at the product state. And epsilon itself is just a dimensionless variable. So if we want to find the change of moles, we just need to multiply it by the number of moles of species I on the product side of the chemical reaction minus the number of moles on the reactant side of the chemical reaction. Now, since and we use this expression here to when we were deriving the chemical equilibrium condition itself by just looking at a reaction itself. But now we have a physical device, and we need to consider the fact that there may be additional species in here that may not be reacting, like we could have argon in here or helium. Those aren't going to react. So we need to account for those moles. And then also, we could have moles in a non-stoichiometric proportion. So say if we had H2 and oxygen in here, we could assume that we're going to burn the H2 with the oxygen, but the equivalence ratio could be say 0.5, meaning we're going to have leftover oxygen. And so this expression here does not account for any of those effects. And so what we need to do is slightly modify it, and saying that the change of number of moles in our container is d epsilon times this nu I double prime minus nu I prime times some constant. And so basically what this means is that we need a multiplier on it, that say if we have 10 kmoles of CO2 in here, as the reaction proceeds, it's not going to consume 1 mole like it would here. It's actually going to consume 10 moles. So we need a multiplier here to basically account for that fact. Okay. So now, what we need is we need a relationship between the number of moles of species I and our reaction progress variable. So all you do is you integrate this, and since nu I double prime and nu I prime are both constants, that is, they don't change as a function of time or reaction progress, and C is a constant. This is a very straightforward integral, where the number of moles of species I is just the number of moles of species I that is initially in our container, plus our constant times epsilon times nu I double prime minus nu I prime. Okay, so here is our chemical reaction here. And so we just note that for, say, CO2, nu I double prime minus nu I prime is actually -1. And we have some moles of CO2 initially in our chamber. So NCO2 would just be that initial number of moles minus our unknown constant times epsilon. And we're going to produce as the reaction proceeds. The reaction itself is going to produce 1 mole, but our chamber may be big or small, so we need to multiply that. We need to multiply that 1 mole by some constant and the C basically accounts for the size of the system. And NO2, we basically do the same thing for that, and nu I double prime minus nu I prime for that is basically 1/2. Okay, and the initial concentrations of CO and O2 are both 0. Okay, so now we need to find this pesky constant C. And so we need to apply the physical condition that as the reaction proceeds, the number of moles of species I has to be greater than or equal to 0. For all, that's what this upside down A thing is. Here, that's the symbol for all I, meaning for all species, and for all values of epsilon. Okay, and so let's look at the extreme case of epsilon is equal to 1. So you basically solve for C for each species and you basically solve it such that if the reaction is complete, that species cannot be less than 0. Okay, and you solve for C. And this only applies to the reactants. Here we only have 1, but if you had 2 of them, you basically apply this condition to both, and you'll have 2 different values of C, and you pick the smallest one of the 2. Okay, okay, and basically what that means, if you pick the smallest one of the 2, that basically means that you're going to have excess of a reactant. Okay, and so you pick the smallest value. Here we only have 1. We only have 1 reactant, and so basically we just solve this expression here. If epsilon is equal to 1, we set ends. We basically say, well, it should the CO2 has to be is going to be depleted if the reaction is complete. And so we just solve this expression equal to 0 and solve for C. And since we start with 1 kmol here, or we start with NCO2 not kmols, the C is just the number of moles of the initial number of moles of CO2. But again, if you had other species in the reactants, like say if I flip this reaction around, and we started with some CO and some O2, you would basically do the exact same thing for both CO or for both CO and both O2, solve for those C's, and then pick the smaller one of the two. Okay, but for this example, there is only one reactant, and we start with just an initial number of moles. Okay, and so if you solve for C, you find that that C is just this initial number of moles of CO2. And so then basically substituting in our value for C, we find that the number of moles of CO2 is the initial number of moles of CO2 times 1 minus epsilon. And as you can see, since epsilon is constrained to be between 0 and 1, this is NCO2 is greater than or equal to 0. NCO2 then is just the initial number of moles of CO2 times the reaction progress variable, and basically and NO2 is half of that. Okay. Then, so now we know the number of moles of each species, and if we look at the formulas that we're going to be applying here, we need to compute the chemical potential. So we're going to need mole fraction too. And so mole fraction is just the number of moles of species I divided by the total number of moles. So then we just sum up the number of moles for all of the species. So we basically add this term to this term here to this term here, and we find that the number of moles in our tank at any given reaction progress variable is just the initial number of moles of CO2 plus, times 1 plus epsilon over 2. Okay, which basically means that the chemical reaction itself is basically adding 1.5 or is adding half a mole to the system as it proceeds. Okay, so and so now this gives us a relationship between the reaction progress, basically how far we are between the reactants and the products, and the number of moles of the various components of the system. Okay, and then if you had some inert gas, say I added some helium here, and which is not part of the chemical reaction, these expressions here are actually the same. Where the additional helium would affect things would be in the total number of moles in the tank, because you basically have to add that too. Okay. So are there any questions on that?
Just so that if we have more reactants, we just do this. If we have more than one reactant, we just do this process again for the second reactant and the third reactant, or?
No, if you have multiple reactants, what you need to do is you need to compute this constant, right? And
right.
Basically, you could, if you have 3 reactants, you could have 3 different values for the constant. But basically, what you do is you pick the value, the final value of C will be the smallest of those 3.
Oh, okay.
Right, because yeah, because essentially because basically the thought process of what we're doing here is we are setting up our system such that as the reaction proceeds, we cannot produce a number of moles that is less than 0, right? I mean, because that makes no physical sense. Okay, so if the reaction is complete, we're basically setting this up so that so that there are no moles left over. And so the different species, if there are 3 reactants, there could be a C for CO2, a C for CO, and a C for O2. And you would just pick the smallest of the 2, or the smallest of the 3, right? Because then that would guarantee that you have the number of moles being greater than or equal to 0 for the entire reaction process. If you chose it, if you chose the largest of the 3 instead, you'd be guaranteed that, say, at some epsilon, say 0.6, then all of a sudden you would have a negative mole fraction of CO2, or a negative number of moles of CO. But it would still be, which would be completely unphysical. Okay. Any other questions? Okay, so now we got a relationship between the number of moles of all the species and the reaction progress, and the total number of moles in the system. We need to go through and now apply the thermodynamic quantity to be optimized. And then we're going to define a function that basically optimizes that based on the moles and are based on our molar relationship that we just derived for our system and the thermodynamic constraints. So recall that the condition of chemical equilibrium is that the sum of ui dni is equal to 0, and also this expression is, or the sum of ui dni is less than or equal to 0. And it's less than 0 if the reaction is proceeding. So we need to examine thermodynamic constraints, and normally those are pairs of thermodynamic variables that are held constant. So for example, if you do a TP equilibration, that means you are fixing temperature and you're fixing pressure. If you do HP, that means you are fixing enthalpy and fixing pressure, so those are held constant. SP, I don't ever see those being used, but you could hypothetically fix entropy and fix pressure. And so then, you have these 2 pairs of thermodynamic variables that you are that you are examining. So for this problem, we have fixed temperature and pressure. So then what you do is you look at your pair of fixed variables, and you go to slide 6, and you look at the TDS relations, and you find the one that is easiest to use. So we have fixed temperature and fixed pressure. So say, for example, we could look at the second TDS relation here. We have fixed pressure, so basically this term crosses out. But we have changing composition and we have real gas effects. So even though the temperature is fixed, the enthalpy in the system may not be fixed. In fact, it is definitely not fixed. So this one is a pain in the butt to use because we have both changes in the enthalpy and changes in the entropy, which is a pain. But now we have fixed pressure, so let's look at the Gibbs free energy version. dP is 0 and dt are both 0. And so these 2 terms cross out, and we are only left with the Gibbs free energy, or the change of Gibbs free energy and the sum of the of dni mu times the chemical potential for all the species. So this is the one that is the easiest to use for our problem. Okay, and so as I just said, for this problem, the Gibbs free energy version is the easiest. So you can basically write that out and then cross out these terms. And now we know that this is that dg is going to be equal to 0 at the equilibrium point. And if you're dealing with an ideal gas, you could use Kp, or the equilibrium constant, to solve algebraically for the equilibrium condition. But for real gases, I find that approach to be a bit of a pain because you have nonlinear solve on top of nonlinear solve. So instead, for when I'm dealing with real gases, I prefer to write a function to either maximize a variable or minimize or basically minimize a variable. So to tell that, what we need to know is that the sum of mu I d and I, if the reaction is proceeding, is always less than 0. So this means that means this quantity here decreases as the reaction proceeds. So basically, these two dg and this term here have the same sign. So if this term is decreasing, this term is also decreasing. And so dg is less than or equal to 0. So this basically means that at the equilibrium point, we minimize the Gibbs free energy in our system. And so the total Gibbs free energy is just the sum of the number of moles of species I, which we derived in the previous slide, times the Gibbs free energy or chemical potential, same difference, they're the same thing, for all the species. Okay, and if you were fixing, say, T and V, you would probably would be advisable to work with the Helmholtz potential. Okay, and so basically you use this expression here and your thermodynamic constraints to minimize or maximize one of the to minimize or maximize one of the thermodynamic potentials. Okay, so are there any questions with that? Okay, so now step 3, this is the part where for an ideal gas, you can do this analytically. For a real gas, you often cannot. So when I say write a function, I'm talking in the general sense where you need to write a MATLAB or Python or something function to be optimized. And so again, this is based on the thermodynamic constraints, and which we did in the previous slide, and the relationship between the number of moles of species I and the reaction progress. So basically what our approach here is, we are writing a function, this function here, not in terms of Ni, because that would basically mean we have, for our system here, we have CO2, CO, and O2. We basically have 3 unknowns. You need to do a multivariable minimization process, which is much more involved than just minimizing one variable. So basically, why we did basically why we did this step here is that the number of moles of each species and the total number of moles are functions of only one variable, and that is epsilon, the reaction progress variable. So we can basically take those expressions, substitute them into here, and we are minimizing a function because, and we know this term, we are minimizing a function of just epsilon. And the mole fractions of species I can also be written in terms of just epsilon. And so we are now minimizing a function of just one variable rather than 3. Which is much more simple, and you can do that any number of ways. Okay, so now in our function that we need to maximize or minimize, again, like entropy is maximized if that's your constraint. Or the Gibbs free energy will be minimized. And now there is a little like gotcha here, is that ideally you could just basically find what the standard Gibbs free energy is for each species, and then write a code that then computes the fugacity coefficient. But there's a bit of a gotcha here when you're dealing with a real gas, because the compressibility factor here in the real gas equation of state, for most of them that I deal with and we deal with, they are normally naturally written in terms of density or in terms of density or specific volume, either or, uh, a temperature, and some variable for a mixture composition, either mole fraction or typically either xi, ni, or the mass fraction of each species. Okay, and so now there's a problem here for our that we have to deal with, is that we know the temperature and we know the pressure, but to compute the fugacity coefficient here, we need the compressibility factor, and the compressibility factor itself is a function of density, which we don't know. So what? So basically, what you have to do then is you need to basically solve the equation of state using for the density using your known pressure. Okay, because you don't know the compressibility factor, and you don't know density. So you need to do a nonlinear solve. If you're using MATLAB or Python for that matter, you can use FSolve for a real gas, and then that basically works. Now this is a bit more doubly difficult if you are constraining, which is very common, if you are constraining H and P, or basically two other variables. Because basically what that means is you don't know density and you don't know the temperature, but you know, but say you do know the pressure and you do know the enthalpy. So basically what that means, if you're fixing enthalpy and pressure, that you need to solve two sets of equations simultaneously for both temperature and pressure. You need to solve the equation of state itself, and you need to solve for the enthalpy of your mixture, and basically forcing temperature and pressure to be the same. And so for an ideal gas, you can solve these by hand. For a real gas, that is not the case. Okay, and so and again, if you wind up in this scenario, again, FSolve in MATLAB or Python is your friend. Okay, so are there any questions on that? Okay, and then the expression itself for the fugacity coefficient, that will be dependent on the compressibility factor for your equation of state. And you can normally find for the common equations of state, such as Peng-Robinson, you can find those expressions. For say BKW, you'll be finding that as part of a homework problem for say homework 2. Okay. So yeah, so based on your equation of state, you do need an expression for the fugacity coefficients. Okay, and so are there any questions with this? So here, just explaining a gotcha is that the fact that you are fixing that you don't know temperature, or that you may not know temperature or density, might mean that you need to solve two nonlinear equations for both temperature and density. Okay, because to compute phi I, you need to know the compressibility factor. Okay. So just in terms of a sort of a code outline, so you would say, I'm just using a sort of Python style header here. So you could define a function. I just called it psi for just a random variable, but you know, in terms of, I would call it G or A or S, depending on what I was actually doing. And that's going to accept epsilon and our two thermodynamic constrained variables. So for our problem, this would be, say, temperature, and then V2 would be pressure. So those are our inputs, and we have the reaction progress variable. Then step one in that function is you compute the number of moles of species I and the mole fractions based on the epsilon relations. Then if needed, you don't always need to do this. You compute temperature and pressure based on the equation of state and your and the thermodynamic constraints applied to your system. So that's basically what's constant. It could be H and P or internal energy and volume, etc. And so and then this will be based on your equation of state, and you can use find root or any other nonlinear root finder. Then after you find T and P, you can compute the compressibility factor. Then you compute the fugacity coefficients. Then after you have those, you can directly basically substitute in the number of moles. You basically know this, you'll know this, you'll know this, and you'll know this. So basically, you then in that function, you can just return the Gibbs free energy. Okay. Okay. Or whatever variable you are maximizing or minimizing. Okay. And so that's the basic outline here. And so step 4 would be to optimize that function to find the equilibrium value of the reaction progress variable. So for our example, if I set temperature to 5,000 Kelvin and pressure to 100 megapascals, and I plot the Gibbs free energy as a function of the reaction progress variable, I get a curve that actually looks like this. Okay, and so the very minimum of this point, or the very minimum of this curve here, is the equilibrium point, and we find that the reaction progress is 0.6315. Then after I know those reaction progress variables, I am then free to go and use the epsilon relations to compute the mole fraction of, say, CO2, CO, and O2. Okay, and then this minimization function, you can use fmin in MATLAB for it if you define a nice function. You can also do it by just making an array of, say, 1,000 points between epsilon 0 and 1, and just finding the index that has the smallest value. So there's any number of ways, basically that you can do this. So you can either use a fancy optimization function in MATLAB or Python, or you can do it graphically by just finding where the plot is the smallest. Okay. So on homework 2, you guys will be having a problem like this, so you guys will be getting some experience doing this. Okay, then now if you do this over a range of pressures, you can find that the real gas equation of state can actually have a significant influence on equilibrium at high pressure, or for any other location where the compressibility factor is significantly different than 1. So here is just a comparison of the BKW and ideal gas equation of state models for our problem, and the temperature is 5,000 Kelvin. So here I'm just plotting as a function of pressure all the way from 1 bar to 10 gigapascals. Again, 10 GPa sounds high, and well, it is high, but that is typical of the pressures that you would see in a detonation condition. Okay, and so this blue line here, that is the ideal gas equation of state, and then notice that as at say 5,000 at 5,000 Kelvin and 1 bar, almost all of that CO2 there's so much energy in that tank that almost all of the CO2 has been split apart into CO and O2. There is hardly any left. Then as we increase the pressure, the equilibrium mole fraction starts shifting towards the reactants, and we start and basically less and less of it starts dissociating. Then up to about 10 to the 8 pascals, the real gas model and the ideal gas model are actually almost the same. Then after that, they start to deviate, and you have the BKW equation of state basically acting like this and producing more and more CO2. Okay, and 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 you can see why they start to separate at that point is that below about 10 to the 8 below about 10 to the 8 GPa for this particular pressure and chemical composition, the compressibility factor is nearly 1, so it's behaving almost like an ideal gas. But then after this point here, the compressibility factor starts becoming quite high, and then that's producing a lot of these deviations between the ideal gas model and the real gas model. Okay, and to explain the effect of pressure even on the ideal gas model, why as we increase the pressure, it's the chemical composition is shifting towards is basically favoring the reactants. We just need to look at our let's see, where's that at? We basically need to look at this expression here, is that even though we are solving for the equilibrium point in a different way, this physics here that we basically learned still applies. And so this Kp is the same for the ideal gas model and the real gas model. And so it's the same for no matter what condition we have in that tank, it's the same. So if we bump up the pressure here, and we look at delta nu here, we know that that delta nu is the total change of moles across the chemical reaction. Well, that is 0.5. So basically, as we increase the pressure, we are increasing this term here. But this term here is not changing. It is fixed. So basically, that means if we increase this term here, we need to decrease this term here. And so basically that means that basically this quantity here, the product of all the mole fractions, it's going to shift towards it is going to decrease. And if you were to expand this out, you would find that it would mean that you are going to decrease the products, which would be on the numerator if you were to expand this out, and you would increase the mole fraction of the reactants, which would be on the denominator if you expanded this out. Okay, and so that's why, and so that is why it sort of favors the reactants. And now, if we were to plug in the fugacity coefficients, which would go right here, for the BKW, those are basically all greater than 1. So you could think of basically the fugacity coefficients being greater than 1 means that the system is acting like is basically acting like it is at a higher pressure than the ideal gas model. And so basically that is increasing so it sort of, you can think of that as almost like it's the real gas effects are like increasing the pressure, which means that for a real gas equation of state, like say BKW, it is favoring the reactants even more than the ideal gas. And so basically everything that this plot here shows is consistent with the physics of basically what we derive for chemical equilibrium. Okay, and so you guys will be doing, I'm gonna be nice and make it a constant volume and temperature to avoid a nonlinear equation solve. But basically you guys will be repeating this exercise here for a different chemical reaction, but for a constant volume and temperature system. Okay, now that's all well and good, but there are thousands upon thousands of species. So how do you do chemical equilibrium with all of those? You don't do it yourself, you use a software program to do that. And how these programs work is they do a constraint optimization problem, is that they have a list of species that they can include, and they know, and you have a starting composition, And you know that the mass of each element, that is the mass of carbon, the mass of hydrogen atoms, etc., by conservation of mass, those have to be constant as the process or as the system equilibrates. Uh, and so essentially what the software programs do is they maximize or minimize the Gibbs free energy, the Helmholtz potential or the entropy, and then they basically constrain it so that the mass of each element is constant. Okay, and so that's part of why I had you when I teach this for this class. I focus on basically minimizing or maximizing like the entropy or the Gibbs free energy. It's because that's more consistent with how the software packages, which basically which you'll be using. And so common chemical equilibrium packages include Cantera. You guys will be using that to some extent for this class. It's not the best for multi-phase for multi-phase mixtures. It has some. It can use ideal gas. They have Peng Robinson, which is under development right now. It's freely available, and it's a Python-based package. There's the NASA CEA. That's a gold standard for mixtures of ideal gases. It's also very accurate and very stable for multi-phase mixtures. Back when I was a grad student, back in my day, we had access to the source code for it, so we could actually run it on our own computers. They don't give that out anymore. I don't know why. And so it's only available via an online wrapper. And the quality of that online wrapper, which I show here, is getting worse and worse and worse as time goes on. And so here you can say, it's sort of hard to see, so I'll just make it bigger. So if you look at this, if you go to CA, if you just Google NASA CEA, you basically, like one of the first hits will be this, and you have to pick your problem type. And then notice that forget about rocket, det, and shock, but notice they have HP, TP, TV, UV, SP, and basically SV. So that is doing a chemical equilibrium problem, fixing H and P or fixing T and P, or fixing internal energy and volume, etc. Okay, and so for one of your homework problems, I'll probably have you use CA and make a plot. But since it's a pain in the butt to use, to get data points rather than going through CA run 100 times, you guys can gang up and basically help each other collect the data because it's a pain. And you guys will know what I mean when you after you start playing with it. Oh, and that's not Cheetah. Okay. Okay, and another one that's sort of it's a Livermore code called Cheetah. That's a very accurate. It has a fairly accurate equation state for very high pressure conditions. It's sort of, and the DOE and DOD labs is sort of a gold standard for chemical equilibrium. It's export controlled, so for class purposes, I can only mention that it exists, and that's it. So I can't give you any homework or like anything with that. I don't even have it. A Tiger, that's a Sandia equilibrium code. The interesting thing about Tiger is it does actually have BKW, which is an equation state you guys are working with in class, or it has what's called JCZ3. That is export controlled. It's also packaged with a code called CTH, which is very difficult to get at a university. And there's also a new code called Magpie at Los Alamos that is currently under development. And it's accounting and it's correcting for deficiencies at extremely high pressures that even Cheetah does not do well. Okay, and that one has shown accuracy up to 100 to 120 GPa. Yeah, I'm surprised that actually to be honest, I'm surprised Los Alamos did not make their own equilibrium code sooner, because for those of you who will get experience working with the DOE, is that there's a bit of a competition between the Livermore folks and the Los Alamos folks. It's kind of a friendly competition, but there is a competition there. So yeah, that's all I'll say for this class on chemical equilibrium. Really, we just did this to really introduce the sort of use of real gases, which for not only these really high pressure explosive-like conditions are important, but for say realistic, like say diesel engines or gas turbine combustors, really high pressure conditions are becoming more and more important. Okay, so that is all I have for this. We might as well stop for today. I will stop recording.